Okay. Okay. Hello, everyone. I'm Francesco Felice. I'm the chair of this session number 24, Visual Display. Okay, we have 5 very interesting presentations this session. And the first presentation is given by Taro Ishii from Tokyo Institute of Technology. And the title of the paper is Ellipsoid, Ellipsoidal Display for Video Conference System Transmitting Accurate Gaze Direction. Just a reminder that you have 15 minutes for the presentation and 3 minutes for question and answers. Okay, so the first presenter.
Hello everyone, I'm Taro Ichi from Tokyo Institute of Technology. Today I will talk about my paper, Ellipsoidal Display for Video Conference System Transmitting Accurate Gaze Direction. For now, face-to-face conversation is still the most frequent mode of communication. So the conventional video conference system has been developed to make remote communication as realistic as face-to-face. However, the planar display you may see right now cannot accurately transmit non-verbal information that plays an important role in communication. For example, turn taking in multi-party more than 3-person conversation is adjusted by eye gaze or gesture. It is reported. The problem on this accurate gaze transmission is because of the Mona Lisa effect. This Mona Lisa effect means that the frontal facial image showing in the left of the picture invokes eye contact perception regardless of the observation direction. For example, both A and B feels their gaze. Meanwhile, non-frontal facial image showing in right doesn't invoke eye contact perception regardless of the direction. So both A and B doesn't feel their gaze. So many studies have tried to eliminate this effect by using the multi-view, by using barometric displays, for example, multi-view 3D display or phase-shift display. However, they need the actuated mechanisms that cause mechanical noises and maintenance issues. And meanwhile, it is also reported that the curved display showing in the bottom can transmit eye gaze more accurately than a planar display. And we also believe that the convenience is also needed for practical video conference system. So the requirements first user independency is required. So unspecified user might use a system, so this user independency is required. And also the head rotation is also required, as the turns face by 90 degrees to look at others is required. And for the convenience, the low manufacturing cost and high reliability is also required. So it is obvious that fewer the driving mechanisms, the lower the risk of failure and manufacturing costs. So our vertical axis symmetric screen looks like the picture. Like picture can display head rotation by changing image without any mechanisms. And we also believe that the similarity of the display face to the real face is also required for the practical video conference system. Both video conference and real meetings are used in today's society. So in this condition, if the display feature image is not like the real one, our users have difficulty to recognize the image as an interlocutor. And it is reported that we identify interlocutors by the overall arrangement of the part as contour of the face. So the display needs to show the arrangement naturally from any angle. Our summary are we believe the three requirements for practical three requirements is needed for practical video conference system: elimination of the Mona Lisa effect and convenience and similarity. So we now propose the ellipsoid ellipsoid display for video conference system, which has a curved vertical axis symmetric surface and the affinity with a human face. So our proposed method, our main mechanism is bottom is a small projector projects a facial image onto the ellipsoid screen via the convex mirror. And there's also movie, so it can move the eye and mouth, and it can rotate the head. Firstly, we made a prototype in the virtual reality environment, which is made with Unity and built on Oculus Quest. And the shown facial image was generated by concatenating the cropped facial image as the center part of each photo, horizontally like this and this. And this facial image will be inverse cylindrical projected on the screen and at the right part of the screen. And the screen shape was also designed from the average dimensions of the face of young Japanese males. And so we also implemented the gaze representation. So firstly, we put the eyeball model on the virtual ellipsoid screen, and this eyeball model gaze at the target point by turning the popularity axis to the target in the left of the picture. And then the eyeballs are projected onto the screen along the popularity axis using parallel projection. With this method, the geometry looks consistent with eyeball models from the target position. So, and we also made a prototype device, which screen is fabricated with 3D printer, and the projector is small laser projector. The convex mirror is spherical mirror. And the facial image for this projection for device was generated by the optics setup virtually in Unity, which is equivalent to the real devices. And for this device, the screen shape was modified. This screen is full-cheeked to reduce the distortion of the 3D geometry of the nose and mouth, and the improves the profile. And we also fill the neck part of the facial image with black to express the contour of the jaw. And this black part of shape of the black part was adjusted to make the frontal face look slender and the contour of the jaw looks natural. And this black part may evoke the Wollaston illusion. Firstly, first evaluation. So we did on the VR prototype for the gaze transmissibility. This evaluation is for the investigation where the eye contact perception occurs from the specific direction. And we want to also acquire the relationship between gaze angle and observation angle, which is, the definition is shown in the right figures. Which gives the perception of eye contact. As a condition, so 11 participants ages 22 to 68 sat and observed the display from 1 meter away in a VR environment. And the participant indicates whether the display gets at them or not by the pressing button for each stimulus, which was made as a combination of the gaze angle and the observation angle, which was presented randomly for 5 seconds. As a result, the number who perceived eye contact for each stimulus, each combination is shown as in right tables. From the table, we can get the trends. The bigger the gaze angle, the bigger the observation angle eye contact was likely to occur. And but however, the gaze angle and the observation angle were not always consistent. We also did the evaluation on the actual device about the gaze transmissibility. This evaluation, So we acquired a precise gaze angle where participants feel strongest eye contact for the some fixed observation angle. So as a condition, relevant participants, 22 to 38, sat and observed the device from 1.5 meter away in the dark room. And the viewpoint was much between them. And so we generated our fixed observation angle from 7 observation angle, which will be presented randomly. For each observation angle, the participants adjusted only gaze angle to where they feel strongest eye contact by changing the gaze angle by pressing buttons. And as a result, for some fixed observation angle, the gaze angle for which the strongest eye gaze was perceived are acquired as this. And the result is similar to result 1. The bigger the gaze angle, the bigger the observation angle, eye contact was likely to occur, but they are not always consistent. As description, so from the results are so the facial image gazing front, which means gazing angle equals 0, which evokes the perception of eye contact only from the front, and the facial image not gazing front evokes the perception of eye contact from a specific range of observation angle. Thus, we can conclude that Mona Lisa effect was eliminated. However, multiple people are likely to perceive eye contact from a single gaze representation when gaze angle is plus minus 81624. So further investigation is required to investigate about that. So we did the measurement of the cone of gaze. So we investigate the range of the observation angle where participants still feel eye contact for each gaze representation acquired in last experiment. The condition is same as experiment last. So the participants changed so the display shows a combination of the observation angle and the gaze angle are represented same as the last experiment. The participants change the observation angle in one direction from the strong gaze representation to the place which they no longer felt eye contact. The adjustments were made to the left and right for every observation angle. As a result, the range of the observation angles the participants perceive eye contact with the strongest gaze representation is like this. So as a result, the angular range width from the given observation angle from the eye point to the border, it was 38.5 degrees on maximum. So we can conclude that accurate gaze transmission is available in conference when the angular distance of the adjacent participant is more than about 38.5 degrees. So the conference, like the right figure, is available with our device. And we also did use the impression evaluation to investigate participants can recognize who is this and how they feel about the image. So the participants rate the display image with visual analog scale and from the right survey. And so the visual analog scale, each mark of visual analog scale was converted into the ratio as a distance from the left end against the total length of line, which means that this value of the ratio is close to 0, which means means the left end, as a ratio of the 1, which means the right end. For the questioner, how do you feel about the face? The average of the ratio were almost neutral. So we can conclude that the impression of the display face are almost neutral. And for the questioner, can you recognize the person? So the average is 0.357 and the median is 0.271. So it is closer to easy to recognize left bird. So more than half of participants can easily identify the facial image as interlocutor. So we can conclude that our method provides a high level of identity between display face and real face. As a conclusion, so we propose ellipsoid and ellipsoid display for video conference system, which can provide accurate eye gaze transmission and convenience to use and the similarity. So as a version of the gaze transmissibility, so Mona Lisa effect was eliminated, and the accurate gaze transmission is available in conference when the angular distance of the adjacent participant is more than 38.5 degrees. And as an inversion impression, so the impression is neutral, as more than half of the participants can easily identify the facial image as an interlocutor. That's all. Thank you so much for the listening.
Okay, thank you so much for this interesting presentation. I didn't see any question on Slido or here on Twitch, so I have one question for you. I didn't understand what is the hardware setup that the person who is displaying in the ellipsoidal display is using. So how do you imagine people using this kind of system?
So hardware setups is there's so this display consists of the ellipsoid screen and the convex mirror and the projector. So the projector, which is placed in the bottom, projects the facial image to the screen, but the field of view is not enough, so we use the convex mirror to reflect the facial image. So only with projector and the ellipsoid screen. So it is this image is now projected.
Actually, what I mean, it's not the setup that you're presenting, but how the person who is displayed into the device will interact with the other people in the room.
So what do you mean? So for the communication, you mean?
Yes.
So the facial image itself is a pre-recorded image, pre-recorded image, and it is modified. And for the communication, so for the sound, so it is close to the current video conference system for the transmission of the sound. And for facial expression, we take the eye gaze or lip tracking with the head-mounted display or something like that, and represent on the ellipsoid screen. It is also already implemented in my display. So in my video, so yeah, it can blink and speak, so it can communicate with others in conference.
Actually, there is one more question.
Yes.
The question is the system only appropriate for meetings where there are multiple local participants or one remote participant?
So it is designed for the one remote participant or one or two remote participants. So actually, so my evaluation is which is hypothesize that there is only one remote participant. It is also for the small scale conference.
Okay, perfect. Thank you so much, and we can go to the next presentation. Thank you.
Thank you.
So, second presentation will be given by Jin-Wook Park from KAIST, and the title of the paper, actually this is a journal paper, it's physically inspired deep light estimation from an homogeneous material object for a mixed reality lighting. Okay, so let's go to the presentation.
Good morning, everyone. My name is Jinwoo Park, and I am a PhD candidate at KAIST UVA Lab, South Korea. The title of our research is Physically Inspired Deep Light Estimation from a Homogeneous Material Object for Mixed Reality Lighting. And I'm really glad to present this work in IEEE VR. So in mixed reality, coherently inserting virtual objects in a real-world scene can provide more immersive experience for users. Currently, many commercial AR platforms, including ARKit or ARCore, are pursuing such realistic mixed reality experience. For this, obtaining real-world illumination is one of the most important key factors. So, in this work, we suggest a novel and effective method to estimate HDR illumination from a single RGB image of a reference object. To solve this problem, deep learning is employed as a core technology. Let me introduce related methods. To obtain illumination of a current scene, the simplest and most exact method is to insert a special camera in that scene. However, it can capture the illumination at a fixed position and may interfere with users' immersion. As an indirect method, a spherical light probe, such as a crumble, was usually used to observe reflected light from it. However, a crumble is a special setup which does not commonly appear in casual scenes. Also, it took an offline process to get HDR information. Other works analyzed reflected radiances from a passive light probe with a specific type of material or a known shape by solving a challenging inverse rendering problem. However, in this study, no additional devices are inserted into the scene. Instead, HDR illumination is inferred from a single image of a reference object through learned regression, covering a wide range of materials and shapes, even without any geometry reconstruction. On the other hand, based on the convolutional neural network, recent works well decomposed a typical RGB image into its intrinsic components, such as illumination. Some methods used an entire scene information as an input, and others observed specific objects as a light probe. However, each method had its own limitation, such as restricted environment or known shape and material of a reference object. In our work, a reference object can be observed in diverse environments for estimating indoor and outdoor illuminations. In addition, illumination can be robustly estimated by covering various types of homogeneous materials and shapes without additional input, such as a depth map or surface normals. Let me talk about our main method. In this work, we have three main contributions. First, we suggest a novel learning-based method with sequential end-to-end deep neural networks that are physically inspired, and it can estimate omnidirectional HDR illumination from a single LDR image of a reference object. Second, we propose an effective approach that gradually decreases dependency on the unknown material and shape of an observed object to cover a wide range of inputs. Finally, a new synthetic dataset where millions of objects are rendered in a physically correct manner with diverse materials, shapes, and environments, including indoor and outdoor conditions. This is the overview of our proposed light estimation method. In the first trial, we found that learning illumination directly from an input object showed low quality results. So our method effectively divides this challenging ill-posed problem into 3 smaller steps. When a segmented RGB image of a reference object is given, in the first step, we estimate incident light information on the object surfaces by decreasing material dependency. In the second step, LDR illumination is inferred as an environment map by learned domain transformation. In the third step, we estimate HDR radiances from the previously inferred LDR illumination. When we linearly interpolate estimated LDR, HDR radiances, we can finally reconstruct HDR illumination. Then it can be used for coherently rendering virtual objects in mixed reality. Let me talk about more details. In the first stage, irradiance.net is designed to extract the average of incident radiances based on the importance sampling on each surface pixel, which is called importance-weighted irradiance. The purpose of estimating this term first is to effectively handle the unknown material terms from the input object observed under the rendering equation. To explain how the importance-weighted irradiance can be obtained, we need to start from the rendering equation. Briefly speaking, this equation explains how radiance can be reflected on a surface point of an object with physical interactions among incident lights, material, and geometry of the object. When using the unbiased Monte Carlo estimation, we can consider the rendering equation as a sum of discrete rays based on the importance sampling. Then, through the split sum approximation proposed by Karis, the sum of incident radiances can be extracted from the complex rendering equation. For a better understanding, the upper figure visualizes the importance-weighted irradiance. When we assume the orange line is the real-world incident radiance into the surface point P, the blue line in the left image and the green line in the right image show the average of incident radiances according to the importance sampling. Even though split sum approximation is biased technique, it can show feasible results when compared with ground truth as seen in the below figure, and we can get importance-weighted irradiance from this technique. To see the benefits of the importance-weighted irradiance, examples with different roughness values are shown in the figure. By using them as ground truth data, in training the irradiance.net, we can extract refined light information from a reference object. Please check the detailed structure of the irradiance.net in our paper. In the second step, illumination.net estimates LDR environmental illumination from the previously inferred importance-weighted irradiance image. Since the dependency on the material was first decreased through the irradiance.net, we can focus on estimating radiances in each incident direction. It requires domain transformation from the irradiance on surface pixels to respective incident lights in the directional domain. Since our goal is performing this without any additional geometry data, such as depth or normals, it is highly challenging. So, we suggest a gradual training technique which is based on the interpolation filter I introduced by Gardner et al. Through this, the network can learn from low to high frequency LDR illumination, while each incident light gradually finds its correct pixel position on the output environment. In the last step, an HDR environment map is reconstructed by combining estimated LDR illumination and HDR radiance values inferred from the third network called HDR.net. To estimate HDR information from an LDR image, we follow the previous method suggested by Eilertsen. In this estimation, we can effectively infer the log HDR radiance in the saturated areas, such as light sources. After the linear interpolation between estimated LDR and HDR radiance, we can finally get the reconstructed illumination to be used in image-based lighting in AR. Our dataset is composed of training and testing sets. Since we employed physically correct rendering technique based on the Cook-Torrance BRDF, we could get about 2 million of realistic training images with various conditions such as shapes, camera viewpoints, types of illumination, and materials. By using our realistic dataset, we can substitute real dataset, which can be hard to get. Please check the learning details and dataset in our paper. Let me show you our results and comparisons with state-of-the-art. These are some results of our method when using synthetic test dataset. In indoor and outdoor environments, our method can infer HDR illumination from various specular or diffuse materials. The better importance-weighted irradiance was extracted, the more correct illumination could be estimated. To evaluate our network performance, we show you results of the ablation study. We use 3 metrics, including PSNR, RMSE, and SSIM to measure the result of respective networks. As shown in the table, when we use the irradiance net and gradual training technique, estimation quality increased well. We compared our method with state-of-the-art by Gogulas et al. And Mecca et al. For more intensive comparison, we used synthetic and real dataset captured in various indoor and outdoor environments. Also, we used different kinds of diffuse and specular materials of reference objects. As a result, our method can estimate better color and structure of illumination, as well as directions of the main light sources. We also compared relighting results estimated from those methods. These results can have important meaning for measuring usability in mixed reality applications. Here, this is our conclusion. By applying our method to various mixed reality applications, we could perform realistic image synthesis using random images from the internet. Furthermore, we could have realistic mixed reality experiences as shown in our real-time demos. In our video, you can check various scenarios using static and dynamic illumination. However, our method has certain limitations to overcome. For example, our method cannot cover more complex materials which are spatially varying or translucent as shown in the figure. In addition, even though using log-scale HDR radiance is beneficial, it is still hard to estimate accurate and extremely high-frequency HDR illumination. Also, our method is affected by incomplete information of an observed object, which has high occlusion or insufficient normal factors. Finally, our real-time system shown in the video also needs advanced techniques, including temporally coherent light estimation. In our future work, those limitations should be handled effectively. This is the end of my presentation. Thank you for listening, and feel free to send me an email if you need. Thank you.
Okay, Jimwood, thank you for this very interesting presentation. Okay, there is one question on the slide though, so I read it. Do you plan to make the model available for others to use?
Okay. Others to use? Yeah, sure. Yeah. You mean the publication, right? Yes, actually, Yes, so we are planning to publish our training data. I mean, the physically rendered training data sets. And also, yes, we are considering that to publish our some codes. Yeah.
I don't see a question. I have one actually. Actually, it's related to the last slide and to the end of your paper. When you say that one of the problem is when you have complex textures. Do you have an idea of how to overcome this limitation?
Complexity?
You already have a plan.
You mean the complexity?
Yeah, the complex textures.
Yeah. So actually, that is very challenging point, and yeah, now we are assuming that the single material, but also we tested our model to the multi-texture object, and actually it showed some low quality results. And actually, there are some related works to segment some different textures in one object. So maybe we can divide some parts into the smaller parts according to the textures, and then we can get some cues from each part of the textures, maybe. Yeah.
Okay. Thank you very much. Thank you again for the presentation and for the very interesting paper. So we can go to the next paper, the next presentation. Next presentation will be given by Jonathan Ventura from California Polytechnic State University. And the title of the paper is Casual Stereo. So casual capture of stereo panoramas with spherical structure from motion. So, Jonathan, you can start.
Hi, this is Jonathan Ventura, and I am an assistant professor at Cal Poly in San Luis Obispo, California. And I'm very excited to present to you our work entitled Casual Stereo, Casual Capture of Stereo Panoramas with Spherical Structure from Motion. I'm presenting this work on behalf of myself and my collaborators at the University of Otago, Louis Baker, Stephen Mills, and Stephanie Zollman. So a stereo panorama is an extension of the traditional panorama that provides a different image to each eye in the VR headset, thus providing stereoscopic depth cues. A stereo panorama cannot be captured by simply taking two panoramas next to each other. This would only provide stereo in one viewing direction. Instead, a stereo panorama provides stereo in all horizontal viewing directions, and you can see an example here as a red-blue anaglyph. So to capture a stereo panorama, we need to spin a camera in a perfect circle with the camera offset from the center while recording video. Image columns from the left and right side of the image are extracted and rearranged to form the left and right eye panoramas. Or alternatively, we can use a specialized multi-camera rig, such as the Google Jump, which has 16 cameras in a circle. And here we use view synthesis to fill in the missing viewpoints around the circle so that we can stitch together the panoramas. In this work, we are interested in enabling what we call casual capture of stereo panoramas, meaning that we can capture it with a single handheld camera, such as a smartphone. Because a person cannot reasonably capture a perfect circle of views with a handheld camera, because they'll necessarily wobble up and down, we use structure from motion to recover the actual viewpoints collected, and then apply view synthesis to render the perfect circle of viewpoints necessary to create the left and right eye panoramas. This process was pioneered by Rickhart et al. In their 2013 paper on mega stereo, and later improved by Bertel et al. In their 2019 paper on mega parallax. So we have found that the use of general structure from motion tools is the major weakness in the casual stereo panorama pipeline. General SFM is not well suited to casual stereo panorama capture for several reasons. First, tools such as the state-of-the-art CoolMap system are slow, requiring 2 to 3 hours to process a scene of several hundred images. But more importantly, we found that general SFM tools are prone to failure when processing this type of video. The small baseline between frames makes initialization of the reconstruction difficult, and as you can see in the video example here, features are only in view of the camera for a short period of time, so it's difficult to find a pair of keyframes with sufficient baseline to initialize the reconstruction. Furthermore, the small baseline between views makes point triangulation and scale propagation unreliable. In this work, we evaluated an alternative to general structure for motion called spherical structure for motion, which I introduced in a 2016 paper at the ECCV conference. In spherical structure for motion, we assume that the camera moves at a fixed distance from the center of an imaginary sphere, with the view axis parallel to the normal of the sphere, so the camera is pointing outward from the sphere surface. In the case of casual stereo panorama capture, where the camera is held in an outstretched hand, we can imagine the user's shoulder would be the center point of the sphere. The camera's translation always is fixed to 0, 0, -1, so that there are only 3 degrees of freedom in the camera's pose, corresponding to the rotational rotation of the camera. As the user spins the camera in a circle, we expect that the camera will necessarily wobble up and down, but these motions should be compatible with a spherical constraint, as long as the camera is always pointing out from the sphere. We won't allow movement in or out, left or right off of the sphere's surface, but such motions should be negligible if the user is being careful to capture a rough circle of viewpoints. In terms of SFM reliability, spherical SFM has several advantages. Because the translation is always fixed, we do not need to do scale propagation. Secondly, there's no ambiguity in 2-frame relative pose estimation, which is a problem in general SFM with small baselines when we try to decompose the essential matrix. So we saw that, for example, with Colmap, when we processed our videos, it would sometimes choose an incorrect initialization of the first 2 keyframes, leading to a failure of the entire reconstruction. And in general, we were unable to reconstruct our video sequences with Colmap. So our spherical SFM pipeline works as follows. First, we detect SIF features and then track them using pyramidal Lucas-Conade tracking, which provides sub-pixel refinement and thus better accuracy than tracking by detection. And that's important for these small baseline images. We robustly compute the spherical relative pose on the feature tracks and only accept a keyframe if we estimate its relative rotation to be greater than 1 degree from the previous keyframe. This allows us to adaptively subsample the input video to make processing faster, something that would be difficult with general SFM techniques. Finally, we perform loop closure on the beginning and ending frames of the video using SIF descriptor matching. Again, using the spherical relative pose. So to initialize the camera poses, we integrate the relative rotations that we estimated using L2 rotation averaging, and that provides a pose estimate for every camera at once, so we don't need to do an incremental reconstruction. Then we initialize the 3D point cloud using DLT triangulation with all the available observations. And finally, we perform robust bundle adjustment, keeping the camera translations fixed to maintain the spherical constraint. You can see here for the Elfin Forest sequence, the estimated camera poses in red, and the point cloud is in blue. In our experiments, we noticed that if the spherical constraint was not used in bundle adjustment, the reconstruction would often diverge and result in failure. So we found that the spherical constraint was critical to robustly producing a reconstruction from such small baseline video. Finally, once we've estimated the pose of all the input keyframes, we use the mega parallax approach to do view synthesis. This approach uses optical flow between neighboring keyframes on the circle in order to inform the view synthesis, and from that we render virtual viewpoints around a perfect circle to produce the final left and right eye panoramas. Here's an example with the Elfin Forest sequence. So on the top you can see the red-blue anaglyph with a nicely stitched panorama. And on the bottom you see a depth map that we've estimated using standard block matching stereo. And so you can see the tree branches are nicely estimated You can see a lot of the depth of the near and far structures here. Here's another example of the children's garden sequence. And you can see some fine structures were estimated well on the left and right-hand sides. And that indicates that the camera poses were well estimated if we're able to get those depths. Here's a sequence taken under the Pismo Beach Pier. And you can see the pylons are well reconstructed. This was a difficult sequence because there was little texture to use for feature matching, and because of the sandy ground underneath us, it was kind of hard to do a level capture. And finally, here's one more example of the Owiho Courtyard at University of Otago, and this is actually where we did the user study that I'll discuss in just a minute. So for the evaluation, the first thing we looked at is the processing time, and we compared our system to previous systems based on the times reported in their papers. So Megastereo uses a single camera like we do, handheld capture. They process about 100 to 300 frames in about 2 to 3 hours, and that's really dominated by the structure from motion processing time. Systems like the Google Jump and similar use 16 camera rig, so they're not really for casual capture, and those work in about 4 to 20 minutes. A recent paper called Instant 3D processes a similar number of images in about 30 seconds, and that's because they use a stereo camera that helps them do the reconstruction faster because they have the depths to begin with. In our system, we use a single camera, so it's the most general, easiest capture process. We process 200 to 700 images in about 3 to 10 minutes, so we're actually faster than all of them except for Instant 3D. Okay, so we found that our system works well on the sequences that we captured, but we wanted to know the real-world applicability of our method. So we did that through a user study, and we wanted to answer 3 questions with our study. What level of training is required for users to produce stereo panoramas with our approach? Do the stereo panoramas produced by our approach appear convincing and natural to the participants? And how will participants perceive the parallax effect in our results? So we had 2 tasks in our user study. The first task was the capturing task, and here we had users capture a panorama first. With little instruction, we just told them to capture the panorama as they normally would. And then second, we gave them more detailed instructions to hold the phone level, outward, and make a complete circle to maximize the quality of the panorama. In the second task, we showed them a stereo panorama produced with our method, and then just a traditional mono panorama with the same image to both eyes in a VR headset. Our hypotheses were, one, that users will find the capturing process for capturing stereo panoramas similar in usability to standard panorama captures, and 2, that users will be more likely to perceive a stereoscopic effect when watching casual stereo panoramas in a VR headset compared to a standard mono panorama. So we had 12 participants recruited from the undergraduate and graduate student pool at University of Otago, 3 female and 9 male, ages from 21 to 31. And all the participants either had experience with capturing panoramas or knew about the process. So first, we had 12 participants, and so each one collected 2 videos, one with little instruction and one with detailed instruction. And out of those 24 videos, 22 were successfully reconstructed by our method. Of the 2 that didn't work, one had focus problems, so it didn't really focus correctly, and the other one, the participant didn't close the circle, so we didn't get a good loop closure. On the questionnaires, participants did not find the capturing process significantly better or worse, comparing the little instructions to detailed instructions. So this confirms hypothesis 1, that they wouldn't find the process any different from a normal stereo panorama capture. And second, participants' perception of the stereoscopic effect was significantly greater with stereo versus mono panoramas. So this confirms hypothesis 2, that we are able to produce high-quality stereo panoramas that give a good parallax effect. Here are some examples of panoramas reconstructed from the participants' video. So on the top, you see one with little instruction, just normal panorama capture. And on the bottom, the detailed instruction where they were instructed to be very careful about the process. And you can see both seem to be reconstructed well with good parallax of the nearby objects. So to conclude, we found that spherical structure of motion enables robust, effective, casual stereo panorama creation with a single handheld camera. It's substantially faster and more robust than general SFM for these kinds of videos. And through our user study, we confirmed that the method works reliably when users capture a panorama normally, just as they normally would when capturing a normal panorama. Finally, I just wanted to note, we did find sometimes that at the loop closure point, the camera might be a little bit higher or lower than it was at the beginning, and this might cause a seam in the panorama, which you can hopefully see here on the right in the detailed view. And so that's something where we wondered if we might be able to relax the spherical constraint to allow some deviation from that hard constraint without breaking the reconstruction. So there might be some way to have a relaxed constraint to still have these benefits, but get a bit more accurate reconstructions in these challenging sequences. So that's an idea for future work. With that, I'd like to thank you for listening. I would like to acknowledge the National Science Foundation and the New Zealand Marsden Council for their support of this project, and just note that code is available on GitHub, and you can also see some examples of our panoramas in WebVR through a headset. Thank you.
Okay, thank you very much, Jonathan, for this presentation. Okay, we have actually two questions. We have two questions. The first one is, what are the practical application in the real world of this casual stereo?
Sure. Yeah. So it's kind of the same use case as creating a normal panorama. You know, on most smartphones have a feature to capture a panorama. You know, just by spinning in a circle. So this is the same thing that you could spin your camera in a circle, capture a stereo panorama. So you get a left and right eye panorama instead of just a single panorama. But you can only view that, you know, if you use like a VR headset. So it's the same as that. You could capture a panorama anywhere without having one of these big rigs like the Google Jump. In comparison to the Google Jump, Google Jump can capture stereo panoramic video because it's, you know, a fixed rig capturing all the views at once. So we can only do a single image, not a video, but it's you don't need that big rig to carry around.
Okay. Second question is, how hard is the spherical constraint in bundle adjustment? How far can the camera path deviate from perfect sphere?
Yes, that's a really good question. We didn't quantitatively evaluate how far you can deviate from the sphere. That's something we still like to do for future work, is maybe capture some sort of like ground truth data set and really evaluate that. The spherical constraint is hard in the bundle adjustment. There's no sort of relaxed constraint that we're doing right now. So like I said, in the end, we did notice sometimes at the end of the loop, your camera might be a bit higher or lower than it was at the beginning. So the reconstruction still works, but when you look at the output panorama, you might have sort of a seam right there. So we tried some different things to make a soft constraint, but we couldn't really figure out a reliable way to do that without having the reconstruction just fall apart in the end. So it's sort of very fragile if you remove that constraint. So it's definitely something for future work to figure out.
Okay, thank you very much, and thank you for the presentation. So we can move to the next presentation given by Marc Gonzalez Franco. This is your third presentation, so you're trained. So Marc comes from Microsoft Research USA, and the title of the presentation on the paper, it's Measuring System Visual Latency through Cognitive Latency on Video See-Through Augmented Reality Devices. So Marc, you can start.
I'm Mar Gonzalez Franco from Microsoft Research, and I will be presenting measuring system visual latency through cognitive latency on video see-through AR devices. Measuring latency is a very complex process, and as systems get more components, it is harder to grasp the real latency, and that's introduced by each different component or modification. First, I want to go a bit on the background and different techniques that have been used for measuring latency. Many of them have been based on this idea of constrained motions, like a pendulum. Created in the 90s. This technique uses a pendulum, attaches a sensor to the pendulum, and then has an external camera that sees both the pendulum and the output of the display. That shows what the sensor is measuring. And this way you can sort of frame count how many frames are there since the pendulum went through the center until you saw that in the screen. There have been instrumentalizations of this and have created these great approaches of this using photodiode LEDs that detect when the pendulum crosses, both on the display side and on the pendulum side. So it's easier to compare both. Newer techniques have facilitated the use on a bit more on the wild, in which you don't need a constrained motion to measure the latency, and they use phase differences on a grayscale between the grayscale you're seeing in the real screen and the grayscale tracked motion you're seeing on the virtual screen. There are more details about this in the paper by Max De Luca in 2010. More recently, with the arrival of high-speed cameras, we've been able to have an observer camera technique, which is seeing both the sensor input and the outdated input on the outside, and that can have a very good way of near continuous latency reporting. But it doesn't really matter which technique you use. The challenges are very similar across the techniques. Different methods return different results. The latency can vary over time because of varying frame rates, or maybe the user looks in a different direction and it has a different rendering load. There is a need to sample over multiple events also. And it's hard to evaluate the latency without hardware, instrumentalizing photodiodes. It seems quite complex. Also, as you add more components, the latency will be accentuated, and some components are not synchronized, so it's hard to evaluate. So we're proposing a new method. The new method is they use the human as the measuring machine. And every VR system has a human. So in theory, if you're able to measure the performance of the human inside the VR environment, you could see whether their performance is showing any latency. For example, what I try to say here, humans respond to outside stimuli on very specific range of milliseconds. For example, visual stimuli are integrated at a neuronal level about 200 milliseconds. The auditory signals are a bit faster, around 100 milliseconds. And there are additional delays in cognition that are added by the response. So if you're asking for people to see something and perform a task, then it will be closer to 300 milliseconds, which is similar to the Ericsson flanker response task, in which people are asked to move in one direction and they move. There is more detail about these different cognitive latencies in our paper. And these numbers might vary a little bit between people, but they are very stable within a person. Like if I take 200 milliseconds to perform on a visual stimuli, that is more or less what my performance. We prepare an experiment to test this idea of cognitive latency as a way to measure system latencies. And we want to also explore how multiple consumer devices are doing, particularly on the aspect of video see-through performance. Like if you want to see through the world, we're interested for multiple reasons on VR on the Wild at Microsoft Research. And we even have our own prototype of see-through device, which is the Prism, which we compare to these other devices that people already know. If you want to learn more about the Prism, there is a website there. So we set up a motor task in which people have to raise their hand from a button whenever the button in the screen changes color. And let's play the video so you can see how it works. It changes colors. They have to raise their hand whenever it's black. And they go through all the different video see-throughs with this test, all the devices and also without HMD. And we measure how long did they take to lift the hand. So of course, we need to compare this to a control measurement that is more similar to the approaches I shown before. And we use this modified outside viewer technique of high-speed cameras. So to do that, we also have created a millisecond accuracy clock. And what we do is we have a camera that looks directly at the clock and a camera that looks at the clock through the VR system. And then the cameras are synchronized through another Arduino, and we capture a frame every 5.5 seconds. We have that going for 30 minutes. With each device, we capture approximately 325 measurements. Of course, only a subset are legible because we synchronize the cameras, but the cameras are maybe not synchronized with the display of the HMD disparity. So sometimes we just catch the black frame of the HMD. And here are the details of the shutter speed, and it's using manual focus. The scene is also very well illuminated. Here more details about the clock that we have created, and also we have open source the code, and you can create your own clock if you want on Arduino board Duo. And basically, I want to show you a very high-speed video of how it looks. Generally, when you're just bare eye looking at it, it only looks like 8888 because it's a microsecond actually accuracy. So, and now it slows down, and you can see the super slow motion video that we created. You can actually see how it's rolling, and in theory, yeah, now it goes back to super speed. At the beginning, you can see also how it's super fast, right? Okay, and let's go. So one thing we need to do is synchronization of the cameras and verify that we have synchronized the cameras correctly to capture at the same time. So we set up this other small setup in which both cameras look directly into the clock without the HMDs in front of them. And we see that both are capturing the SAC-save number. That means that they are synchronized. So once we have that, we put the HMDs in front of one of the cameras. These are the results. So on the cognitive latency side, let me see if I can highlight things here. Yeah, so on the cognitive latency side, we have the baseline, which is how fast people were with the PC only, releasing the button. And this is between 300 and 350 milliseconds that, if you remember, that is kind of, here it is the exact response time. That is kind of what the literature shows on motor tasks, rapid motor tasks like the RxM Flanker. So that is a good validation. And then we have the response that people have on the different HMDs, right? What we can do is we can take the baseline out of the different devices, and then we end up with because the baseline is how long does the motor system work for a person, how long does it take to respond, and then that could be the baseline for the other ones. You can normalize and find out the exact latency that, or infer the latency of the system, right? And here we can see this inferred latency is basically each of the devices minus the baseline, So here we can see the inferred latency using the cognitive latency. And we also have the measured latency that we measure with our clock and the observer approach. So, few things. Here we see all the latencies across the different devices and methods. Details on the significance of these are on the paper. I have to say that the index is giving a bit higher latency because of how, in Quest and Rift, the camera goes directly into the screen of the HMD without going through the computer. In the index, what we did is we retrieved the images from inside Unity and then re-render them in Unity, which of course is going to take longer. That same technique was used with the Prism, but the Prism is a device that was designed to do that. And you can get more details, as I said, on the Project Prism in the Microsoft Research website. So a few things that we find from the infer, the cognitive latency versus the measure photon-to-photon latency. First, we don't find significant differences between the methods. So whatever we found on inferred was comparable to whatever we found on measured. And you can already see that here. There is a larger variability on the variance for the infer method that may go away as we increase with more participants, because different participants will have different latencies themselves and in the performance of a task, and over a larger data of participants, I think that would converge into closer to the measure data. And then regarding of the latency, we were able to rank them, and the Prism was the top performance. Then we had the Quest, the Rift, and the Index. So those are the results, which I think are also interesting in terms of knowing which devices are the best performers. I think this new method of cognitive latency contributes to the general challenges of measuring latency. I think, first of all, there could be maybe a standardized task that we could find that will help compare the different methods up to now and how they compare to this cognitive task. Maybe attaching the sensor to the pendulum and then showing whatever the sensor shows in VR, and that's the trigger for the motor task, or maybe something else. Another good thing about this method is that we can measure over time in a continuous way how people are performing to a task. Maybe something like Beat Saber, you can see whether people are, the latencies are changing over time. And you can do it in a very large way because you don't require new hardware to instrumentalize every single device. You just require a human, and every VR system already has a human. And it might be easier to check which components create latency because you know what the person is doing at the same time as the latency is being retrieved. So you could figure out better ways to figure out the different components that are introducing latency. Finally, a conclusion slide. Very simple. It's an easy method without the additional hardware. It can scale to crowdsource. And it can measure online latency. Is it increasing or decreasing over time in this particular task or system? And one of the things that we believe is that there are more possible tasks to be used for other types of devices that are not video see-through. Like I mentioned, the instrumented pendulum can have a counterpart VR task that you need to perform, and it doesn't need to be properly a video see-through. And with that, we can go into the questions. Thank you.
Mar, thank you for the
Yes.
presentation. There is one question on Slido, is how you would probably have different latency depending on the age of the person in the HMD, right?
Yeah, well, it's not only the age of the person, like different people will have different latencies. More or less, everybody merges towards a center of latency. That's why for this experiment, we did it within subjects. Every subject ran through all the devices, so we can compare the devices nicely. However, I think that if you have a very large number of participants, you might not need to have everyone go through all the devices. You can assume that the demographic will be similar across all the devices, like in SteamVR. It doesn't matter which device you're using. Probably you have a large enough number of people that your variance in the particular latencies that a person might have a difference within with another person, that will sort of disappear.
You use the Arduino, right, to control two cameras. Did you check if the Arduino introduces some latency? Anyway, you can remove by removing the...
So one of the things we did, and that's why we control by taking a picture of so we used two Arduinos, one for the clock and one to synchronize the cameras. Okay. We did find that sometimes one frame will slip. It was very easy to know that because it, and then we calibrated very well. I mean, at the end, we didn't have any slip frame from the synchronization. It was very easy to find that because you would see that the clock was different on the both pictures. So I think it's not that hard to calibrate both when you can control both parts of the system.
Okay, I don't see any more questions. So thank you very much, Mar.
Thank you.
And we can go to the last presentation. So last presentation is given by Shanglong Feng from Rutgers University. So the title of the paper is LiveDeep, Online Viewport Prediction for Live Virtual Reality Streaming Using Lifelong Deep Learning.
Hello, everyone. My name is Xianglong Feng. I'm from Rutgers University. Today, I'm going to present our paper, LiveDeep, Online Viewport Prediction for Live Virtual Reality Streaming Using Lifelong Deep Learning. This work is done with Dr. Yao Liu from SUNY Binghamton and my advisor, Dr. Sheng Wei from Rutgers University. VR streaming applications are getting popular. YouTube and even the non-technical media, such as National Geographic, provide a huge amount of high-definition VR video content. Those videos provide a unique user experience. By wearing a head-mounted device, you can have the feeling of being in the scene. Look at the video clips above. You can feel like you are standing very close to Kobe, which is a much better experience compared to the traditional video streaming, where you can only watch what they show to you. For the video clips to the right, you can feel like standing in the sports field, standing to the athlete even closer than the audience. Most of those videos are from video-on-demand system, where the videos are stored on the server. The most promising work is a live VR streaming for sports events or breaking news. However, given the demand of high resolution and high frame rate in VR streaming, the live VR streaming application are facing significant bandwidth capacity challenges. This is a demo for a typical VR view. The left image is the original video, and the right one is the view that the user sees in the HMD. When we compare the two images, we can see that the user view is only a subpart of the whole frame. Some research works analyze that for a full key VR video, the sphere only has 10 pixels per degree, and the actual user view only equal to a 240p on a TV screen. In another way, the overall resolution of the whole video frame is much larger if the user's actual view is displayed with high resolution. As a result, the video size could be very large, and it will consume higher bandwidth compared with the traditional 2D video. Some work study that HD VR video requires 400 megabytes per second. To solve the bandwidth challenge, researchers proposed the selective streaming method. One typical selective streaming implementation is built on tile-based encoding. The video pipeline is shown in the above figure. The captured video will be encoded and packaged in a small video segment for distribution over the CDN network to the client. The HEVC video encoding now supports independent encoding. The video frame could be equally divided into small parts. Each part could be encoded independently and simultaneously, as shown in the second frame. What's more, each part could be encoded with different resolution. As can be seen in the third frame, in each tile it is labeled with H and L, representing the high resolution and the low resolution. So, assume we select the center part of the frame as the chosen part. We encode the center part with high resolution, and encode the rest part in low resolution. As a result, the video size is reduced in the distribution step. If the selection of the tile is correct, the user could see a high-resolution video. If not, the user could see a low-resolution video. So, it is very obvious that the major challenge is the viewport prediction. Currently, there are three types of viewport prediction methods: the trajectory modeling, the heat map-based methods, and the motion-based method. The trajectory modeling leverages the user trace on one video to predict how other users watch the same video. The heat map-based methods will first analyze the historical user trace data. They will draw the user trace heat map for each frame in a video as a hint for predicting other users' viewport in the same video. The advanced method will train a neural network model based on the video content and the historical user trace. This neural network model has similar functions as the heat map. The last type is the motion-based method. This method assumes that the user wants to watch the moving objects. So, this method predicts the user viewport by using Gaussian mixture model and optical flow for motion detection and estimation. Although those methods are effective in VOD system, they are not yet ready for live streaming system. It has three unique features. First, the video content is generated on the fly, and no trace of previous videos can be used to train a prediction model. Second, we cannot predict the viewport based on previous users' head movement. And third, viewport prediction should not incur significant processing delay. According to the three unique features, the heat map-based method would fail since no video and user data is available. For the trajectory modeling methods, the prediction accuracy would become worse for longer duration, such as a video segment. The motion-based method is easily impacted by the dynamic background, so it will enlarge the bandwidth consumption. So, due to the three features, we develop a novel online viewport prediction method targeting live VR streaming, namely LiveDeep, which follows the three design principles. First, online. The prediction model should be generated online to accommodate for the live video content generated on the fly and the associated user preference. Second, lifelong. The prediction model should be updated periodically for the entire video viewing session to accommodate for the potential changes in either the video content or the user preference. And the last but not least, real-time. The processing delay caused by the viewport prediction algorithm should not compromise the desired frame rate and the live streaming latency. This figure shows our LiveDeep framework. It contains the video pipeline and the viewport prediction method based on both CNN and LSTM models. We treat each video segment as the basic processing unit. The red rectangle labels one video segment from the whole video. In this unit, we predict the user viewport and train the LiveDeep model. In our work, we set the video segment duration as 2 seconds, following the dash-based streaming standard. In this figure, the red rectangle shows the subsampling of the frames. For each video segment, we uniformly subsample 8 frames. We do this based on 2 considerations. The first one is the potential processing delay, introduced by a huge amount of video frames in each segment. So fewer frames means fewer processing time. Second is that we think the video content between adjacent frames in 2 seconds is similar. So we do not need to process every frame. This part is the collection of the training data, which is done in the runtime. In each selected frame of one video segment, the frame is uniformly divided into 5 by 5 parts. So, for every video segment, the input images for CNN network are 200. Also, we collect the user feedback to figure out which tile the user viewport center lies in. The detailed information will be discussed in the CNN and the LSTM section. As we mentioned, we use 2 deep learning models, the LSTM and the CNN model. We use the CNN model to recognize which tile have the video content that the user wants to watch, and we use the LSTM to predict the tile that the user viewport moves to. So, the LSTM is based on the user trace. The union of the 2 prediction result sets will be used to generate the final prediction. Now, we will discuss the detailed implementation of the CNN model. Because the video and the user trace data are not available in the live streaming system, we have to modify the traditional CNN application flow. Here are the modifications. First, which is also the most obvious one, the processing order is different. For the traditional deep learning, we train the model first, then we test it. We will use it after the performance is good. In the live VR streaming scenario, we first use the collected training images to infer the user preference, doing forward propagation. Then, we collect the user feedback to check the prediction result, calculate the loss, and train the model using backward propagation. Second, only 2 outputs. There are only 2 classes in the output layer of the CNN model. One represents the class that the user is interested. 0 represents the class that the user is not interested. Third, we label the images in the runtime. Those collected images in each video segment are not labeled and cannot be used in supervised learning. In the runtime, we compare the images with the center of the actual user viewport, and label them as interested if the center of the actual user viewport is covered by the images, or not interested if the center of the actual user viewport falls outside the images. Third, we label the images in the runtime. Those collected images in each video segment are not labeled and cannot be used in supervised learning. In the runtime, we compare the images with the center of the actual user viewport, and label them as interested if the center of the actual viewport is covered by the images, or not interested if the center of the actual user viewport falls outside the image. Besides the previous change, we made other modifications because of the special conditions. First, considering the processing time is limited, we set the maximum epoch as 10. We also find that, with such limited data, we cannot improve the performance by adding more iterations. Also, we find that the prediction accuracy will not improve after the loss value is lower than 0.2. We will terminate the training once the loss value is smaller than 0.2. Second is the batch size. Considering the limited training data and the processing overhead, we did not further divide the training images into smaller batches. So, in our work, the batch size is 200, which means we will process all the input data in one loop. Third, we set a dynamic learning rate based on the loss value and the coverage rate to further reduce the training time. The coverage rate is similar to the IOU, meaning how much predicted area covers the actual user view. Last, despite all efforts, we found that the output of the CNN model will treat too many inputs as interested. So, we collected those labeled as interested by our CNN model and sorted them based on the output score. We set a threshold M to select the top M tiles. The LSTM part is more like the traditional deep learning application. We collected the user trees in the previous video segment, which consists of 8 sample points from the 8 subsampled frames. The 8 sample points are collected as the training data, and we assign the index of each frame to each sample point as the time step. Finally, we train the LSTM model with the collected training data and infer the user viewport in the next video segment. We implemented the LiveDeep on a Dell workstation with 2 CPUs and 1 GPU. We adopt PyTorch to implement the CNN and the LSTM modules, and use CUDA to accelerate the deep learning processing. We use OpenCV for video processing. We evaluate our LiveDeep using 14 videos and the user's head movement traces from a public dataset. Each of the videos is watched by 48 users. We evaluate the prediction accuracy by using a correct-incorrect labeling method. For each frame, we compare the predicted viewport with the actual user view, and treat the prediction as correct only if the actual user view is completely covered by the predicted viewport. The prediction accuracy is then calculated by the number of the correct frames over the total number of the frames in the video. We adopt 2 test cases in our evaluation to cover both the basic single video viewing experience and the lifelong scenario, concatenating multiple videos of different types. This is the prediction accuracy over the 14 test videos. As we can see from the figure, LiveDeep and motion-based methods achieve similar and high prediction accuracy, which is around 90%. Prediction accuracy of the LSTM and the CNN method is low and varies in a large range. This is the accuracy for 2 test cases. It can be seen that single video case and the lifelong case share similar prediction accuracy. The LiveDeep method is robust in the 2 test cases. The user trees-based prediction method usually uses a fixed prediction size, so we only compare the bandwidth usage for CNN, LiveDeep, and motion. As can be seen in the box plot for bandwidth usage, CNN and LiveDeep achieve similar bandwidth efficiency with a narrow range of distribution. The motion-based method results in a huge variance in the bandwidth usage. We draw the CDF figure for the processing overhead for all testing videos. As can be seen in the figure, most of the processing overhead is less than 1.2 seconds. This is acceptable for a 2-second duration. In summary, we developed a novel viewport prediction approach, namely LiveDeep, for live VR video streaming. By adopting hybrid prediction model and modification to the traditional supervised learning workflow, it solves the no historical video user data problem. The experimental results show that LiveDeep could achieve high prediction accuracy with premium bandwidth usage and short processing time. This project is sponsored by the National Science Foundation. Thank you for listening. You can find our code for this project on GitHub, and the link is posted below.
Okay, thank you, Shanglong, for the presentation. We have quite long questions, so okay, let's split the question in 3 parts. So the question is, how would a system like this be deployed in production?
Actually, if you look at the slides, it's like we need to implement this on the server. So actually, this should be integrated with the Dash-based streaming. when you integrate with this, it's like you can use some hint to encode it with some file description along with the each video segment. So you can tell in which part is, let's say for some video, some part is low resolution. For some video, some other parts is high resolution. So users can select this based on different preference. So this is how we're gonna implement this.
Okay. There is another part of the question. It seems like your model needs to run on a user machine and not on the server client system.
Actually, no. It should be in the server. If you look at the slides, actually the server will collect the user feedback, because every time the user will send the request to get the new video segment, so we can collect some user feedback, and on the server the user this algorithm can collect the user obtain the user feedback and predict the user view based on this feedback. So that is how it works. So I think the question is like, when we implement this, how our algorithm can work with the server part. So basically, as we know, it's like we should provide some hints in some description files, which will help deliver some small video segments. So that is how it should work. And actually, that is also our future research work. So we have this prediction algorithm. Then in the next step, we want to kind of build this live streaming system.
Okay, thank you very much. I don't see any more questions, and actually we are 1 minute late, so I think we can close this session. Session number 24, visual displays 2. So thank you very much to all the presenters, and thank you very much to all the people that were attending the session. Okay, bye-bye.